Okay, so welcome to the ultimate class. This is the last one. There are no more. Um, so just a few business items before we dive in. Um, please make sure that whatever latest thing you worked on has been uploaded either to um, wherever it is that your group is keeping things. So the GitHub repositories for the Traveling Salestronaut and the Galaxy Mergers group and or groups and the and Maria, right? The workspace on Maria for the Canopy Waves folks. That way we have it, we can do things with it. The final is Tuesday from noon to 2. Having heard no objections, we're going to go with that. Each group will have about 25 minutes to present. You're welcome to use your poster, cannibalize your poster into a presentation, make a poster and a presentation, whatever you think would be the most useful and interesting. And remember, of course, that everyone has been seeing bits and pieces of what other people have been doing. So, you can feel free to sort of dive into more depth. Oh, excuse me. Dive into more depth than you would have, like in, say, the poster session. Because instead of talking to biology majors, you're going to be talking to each other. Any questions about the final exam? We'll do the air quotes on it. Okay. The one other thing I wanted to mention, so I know almost nothing about this, but I got an email yesterday saying that Chico State is running something called the, and I'm going to mess this up because it's a Spanish word, but Adelante program. Anyway, it's basically a summer research program. So it's kind of like a PSRI type thing. We weren't planning on doing any PSRI this summer, but this one is, it's better. They're offering more money than we do for PSRI for the students. They're offering some funding for the faculty that participates, and frankly, it's the kind of thing that I suspect what happened is they had some pile of money that they could only use for giving to students, and they didn't know how to spend it, and so they invented this thing. It's not like a STEM thing, it's campus wide. And so I have no idea how many students are going to apply to this, and it's obviously extremely late in the game for this. I imagine most of you already have summer plans made, but I posted the PDF that they sent out on the Slack channel. And if anyone's interested, let me know. Generally speaking, I wasn't planning on having any summer research students this year. But all of you are nice enough to work with that, and we're already sort of up and running, that I think it would work fairly easily to continue on with your project if you wanted to over the summer and get paid for it.
Dr. Nelson, is this something that I qualify for?
Yes, it is. So any current sophomore, junior, senior, or graduate student in good academic standing at Chico State can apply, even if you're graduating. So yes, Sean, you could do this.
I'm filling that out right now before I forget.
So basically, as far as I can tell, anybody can do this. So hold on, Sean, before you actually fill anything out, let's see how many students are on this thing, and then that'll determine what we have to write. Each faculty member can mentor up to 3 students. So if all of you want to do it, then we're going to have to pass out knives and let everybody, fight to the death or something. But if 3 of you want to do it, or fewer, then we can make that work. So anyway, like I said, I have no idea if, 500 people may apply for 20 spots here, but I suspect that we'll have a fairly compelling case because you guys have already been doing research with me, and what we're doing works very nicely with the whole, coronavirus restrictions. So anyway, I know Dylan expressed potentially some interest. Is anybody else interested?
I'm definitely interested.
Okay.
I would be interested too. I've been wanting to like continue that other project that I started with.
Okay. Well, let's do this. Why don't we? I'll send out an email, or I'll probably just post it on Slack, and we'll get sort of a head count of who all's interested and what they would be interested in working on, and then we'll try to figure out how to massage that into whatever the program wants. So. Okay. The one other thing I was going to mention is that if you are interested in continuing working on this stuff outside of that summer thing, but potentially in the fall, I will be able to do a $4.99 class, right, as I've done previously. So if you'd like to, work on something and you'd like to get course credit for it in the fall, that's a possibility too. We'll need to figure that out before classes start in the fall, but we don't need to figure it out right now. We don't even know if we're going to be on campus in the fall yet. So we'll figure it out as things get closer. But keep in touch and, keep using the Slack channel. Okay, any other comments, questions, concerns? All right. Well, let's end out doing some machine learning stuff. Oh, before we get started, before I let Cindy get started. So in poking around, let me share this. I found what I believe is probably the most useful thing I've found on machine learning yet. And it's this basic, this decision chart that basically gets at machine learning options. Now, this is specifically machine learning within scikit-learn, which is not the only library out there. And it is missing some pieces that one could use. But all that aside, this is sort of a good starting place. So it's just one of these decision charts, and it goes through what we're doing. Usually in physics, what we're interested in is the regression side of things. We want to predict a quantity, okay? So we're generally not interested in predicting a category. Like, for example, the example that we're doing is digits, right? Which is just trying to sort things into categories. Generally in science, we're interested in putting things in actually making a model that predicts a quantity. And so we won't even get to some of these, but there are some options in here about, you could use, all these sorts of things, right? Lasso, elastic nets, ensemble regressors, all kinds of stuff, right? And each one of these things you just sort of have to hack your way through. But the point is that they're all, they're all options to consider. And by the way, Sean, I feel like now I understand principal component analysis much better than I did a year ago. And it's taken longer than I would have liked, but I think I finally gotten to a point where I feel happy about how I feel about principal component analysis. So, okay, with
Honestly, me too. Me too, Dr. Nelson.
that, good. So with that, I'll stop talking and let Cindy take over and tell us all about
Yes.
whatever stuff.
Okay. I stayed up all night just so that I'm not late, and so that I don't I'm not like super sleepy right now. But anyways, I did this for you guys, so let me go ahead and share my screen. Oh, you have to enable screen
Oh.
sharing.
I always forget to do that. All right.
Okay, so I put it all in my Spider IDE. Okay, so I started off, I took notes. I don't know if you guys take notes, but I can't wing it. Wait, can you guys see the plots that are, no? Okay.
No.
Let me stop sharing just that and let you guys see everything that I can see. Okay. So I actually wrote this program myself. Like I didn't know that, like I couldn't get the one in scikit-learn to work. So then I ended up doing this, but we already saw this, so like it doesn't matter. And then let me see what this is. Oh, I think Nelson also showed this part. So I don't know what this is. Hold on, I don't know where I start. I think we saw this already, so we don't need to look at that. And then,
Let me just say with the PCA, could you bring the PCA plot back up?
yes.
Because it's worth looking at. I'm not sure we actually looked at the plot last time.
Oh,
Before-
I think it was because of you couldn't get this to work. So I think you were importing this, but it had to be PCA as this. So that's why it wasn't working. But I looked it up and I got it to work.
Yeah, so it turns out that they combined the randomized PCA and PCA in one of the more recent scikit-learn releases. And so the code that they had, that the web page had, actually didn't run on the more recent version.
Okay.
And it turns out that what they actually did is now the PCA thing automatically chooses whether or not to do the full, analytic thing or do this randomized version that gives you a good approximation. One of the things about data science is that they tend to think like a normal size data set is like, 1 billion entries or something. And so they're very interested in approximate methods that can run very quickly, which is what the randomized PCA is. Oh,
Okay.
but what I was actually going to say is you can already see that even so what the PCA does is it's reduced this thing from a 64 dimensional space, right, to a 2-dimensional space. And you can already see that it's doing a really good job with most of the digits, right? Like the zeros are all clustered in one spot and the 7s are all clustered in one spot and the 4s are all clustered, right? Now, there are some it's obviously having trouble with. It's having trouble with 8s and 5s, and they're kind of landing on top of maybe, I don't know, those are 6s and 2s, and anyway. So you can see there are some that you can't just get by doing the principal component analysis. But just doing the principal component analysis and looking at it by eye, you already can see that there are some pretty clear clusters in the data. Which is weird, right? It's weird that you can reduce this from an 84 dimensional vector space to a 2-dimensional vector space and already get 6 out of 10 digits correct.
Mhm. Okay, we're gonna move on. So in this block of code, we import scale. Well, actually, so we're gonna be talking about k-mean algorithm, the k-mean algorithm. It's the simplest and it's the most widely used learning algorithm for solving clustering problems. The K in k-mean means the number of clusters, and that's something that you pick, the website said that you pick randomly. In order to use the k-mean algorithm, you have to have more than 50 samples, less than 10K samples, labeled data, and you have to know the number of categories that you want to predict. So the steps, the algorithm finds the nearest cluster center for each data point, and it assigns the data point closest to that cluster. So once all the data points have been assigned to a cluster, the center of the cluster is computed, and they call it the centroid, I think that's what they call it. Okay, so in this block of code, I think that the IN stands for index, I'm not sure. So we're gonna, I already ran it, but scale, what scale does is that it standardizes the data. So it standardizes the data set along any axis. So by scaling, we shift the distribution of each attribute to have a mean of 0 and a standard deviation of 1. And right here, what this is doing, so I'm just gonna go ahead and run it, is that it splits the data. So so they say that we usually split the data, the training data into 2/3, and then the testing data into 1/3. I'm saying we, but I mean, I don't really know what, I've never done this, I don't know what I'm saying. And then the test data is just set to a quarter. And then the random state is 42. Scikit said that they use 42 so that we can get like reproducible results. I'm assuming that they're talking about test data and training data so that they can be like similar or something like that. And then this is so that we can analyze the samples. So let me see. So there are the X train and the Y train, which is like the X and Y training data, has this many samples. And then 64 features that haven't changed. I don't really know what they mean by that though. And then the X and Y test data, yes.
So the 64 is the number of pixels, right? In the image, because it's each image is an 8x8 grid, so it's effectively a 64 things, right?
Okay, I see. Okay, and then the X and then the Y testing data also has this many samples in it. Okay, so right here we import cluster. We use the k-means. The init is just so that you can like initialize what kind of method you want to use, even though we're putting k-means even though it's already k-means. If you don't put anything, it's going to default to k-means, to the k-means algorithm. We are setting the number of clusters to 10. So we're setting the number of clusters to 10, but then that also means that there's going to be like, that this number also corresponds to how many centers there's going to be. And then the random state is also 42, which is the 42 that you see up here. And then this is a fit the training data to the model. It didn't really talk about this. It just, this description is all that they said about it. I don't know if I've ran it, so I'm just gonna run it again. Okay. And then This is,
So let me just say something real quick about what it's doing there. So the way that this algorithm works is that it chooses, well, okay, so it can work a number of ways. The simplest way to think about it is it chooses 10 in this case, random places in this 64-dimensional vector space. And then as the centers of its clusters, right? And then it basically goes and looks at, okay, how many points are closest to each of the cluster centers? And then it adjusts the cluster centers in order to minimize the total distance.
yes.
So what it's doing here is it chooses random. It can choose random points. The k-means plus plus thing is just saying, okay, choose intelligent points, right? Because you can imagine in a 64-dimensional vector space, you could choose at random some pretty stupid initial configurations, right?
Mm-hmm.
Like, just think about it in a 2-dimensional space. If we had, if we, picked all of our centroids on top of each other and then one way off to the side, then that's bad, right? So then what it does is it goes through the algorithm, it goes through this iterative process where it figures out, okay, which of these centroids is too far in one direction and shifts it, right? And so it goes through and shifts the centroids. But as you could guess, this is very sensitive to the initial selection.
Right. Yeah, that's what it said. It said that that was like one of the disadvantages of this algorithm is that the initial set of cluster centers has an effect on like the clusters that are actually found, and that to like deal with this, we want to try several initial sets and multiple runs of the same program, just so that to minimize the distance between each point in the cluster, so it could be closer to the mean. Yes. Okay, so are you guys ready to see a plot? Yay! Okay.
So wait, hold on. Bring that back. Bring that thing back.
I'm
That was
sorry.
good. Okay, so what did it do? Somebody other than Cindy, what did it do?
You guys had homework. Come on, guys, even I'm awake.
I can get my 4-year-olds in here. They're really good at identifying numbers.
Unmute someone's mic.
Okay, come on. What numbers do you see?
0, 1. I think this is 3.
The bottom left is a 5.
Yeah.
Top right is a 6.
Maybe a 7 right here.
Is it maybe like 1401657? Yeah.
So it was trying to figure out all the digits, right? It was trying to figure out all the digits from 0 to 10 or to 9, right? And we didn't tell it what those were, right? We just fed it a bunch of digits and said, find cluster centers, right? So find places in this 64-dimensional vector space that are the center of clusters of data, right? And so you could imagine if we had fed it every image being exactly the same, that it would have generated the numbers we gave it. Not in the right order, right? It doesn't know that this is 0, that we think that should be the first one, right? But it would find a 0 here and a 2 there and a 6 there. And I don't know what happened you know, in the bottom left corner there, but somehow it got lost, right? It never found a 9. It got lost and found some weird thing. And I don't know what happened. It looks like it may have gotten 2 different ones and never found an 8. Right? So it's not perfect, right? But it did find some things that you wanted it to find, which is nice.
Dr. Nelson, I think, and I kind of figured this out when I minimized the Zoom chat, but like, if you look at it from very far away, it looks like the bottom right could be a 9 from really far away.
Okay. That's the 9.
This one?
No, he said bottom right, so he means that weird one with the black in the corner. I'm not seeing it.
It's weird that the bottom right is like so like discolored, or not colored because none of them are colored, but so like, you know, much brighter than all the other ones. They just put a big black dot in the corner, basically.
So let's run this again, but give it a different random seed.
Where do I do that?
Go up. So when you did the
Right here, right?
k-means,
Oh, this one?
yeah, instead of giving it 42, give it some other number. Great. And run that, and then run the next one. Okay, so by giving it a different guess, it picked different things, right? And you know, it looks like it got the 3 and a 4, and then I don't know what the next 3 are. And then a 0, and then maybe a 7, and then a 6 in the bottom right, maybe.
Mm-hmm.
Right? So that one was worse, right? Because that one, I can only identify 5 digits on that one. Maybe one of those is a 1. That's kind of weird looking. So do you see what he was saying about trying a bunch of different versions? Right? Because the quality that you get depends a lot on that random initial guess, right? So in physics, we would say that this is very sensitive to its initial conditions. All right, keep going.
Chaotic.
Yes. Yes, it is. It absolutely is chaotic.
Okay. So right here, the Y pred is like it's a prediction of the values for the test set, which has 450 samples. And then we're just printing these right here that once I run, you guys will be able to see it. And it says it studies the shape, but doesn't like print out the shape or anything like that. But this ISO map is, it's another method, I think. It's another method. It's to reduce the dimensions. So it's different from the, what is it called? The first one, it's like principal component analysis, because PCA is it's a linear transformation, and the ISO map is a non-linear reduced method. So I'm just gonna go ahead and run that for you guys. And then, how do I make this? Okay, I won't do that. So this is the first 100 instances for the predictions and then the tests. And this is using the ISOMAP. That's what this is, the training, and then, well, this is the predictions, and then this is the actual, so like the real points. And then
So,
it's
so if I can jump in again, if you look at her data, what actually printed out, right? The second set of stuff that got printed is the actual number, the digit, right? And the first set is the cluster closest to that particular data, right? The prediction. So you can already see there was a mistake. It confused a 9 and a 3. Because if you look at there, it said that in the actual data, the prediction set, or I'm sorry, the prediction, the top row, said that the second and third entries were the same digits, right? They were both entry number 0. And again, that doesn't mean they tried to make the digit 0. Just whatever came out on the 0 of the plot, right? The first cluster center. But you'll notice it said that the second and third were both the same digits. And if you look down on the actual data, you'll notice that one was a 9 and one was a 3. So it screwed up, right? It confused a 9 and a 3. And you can find more of these, right? If we went through and looked at all of the things that it thought were 0, right? We'll see it thought a 9 was a 0, a 9 was that, a 9 and a 3 were the same, and then a 2, and then a 3, and then an 8, and then a 9, and then a 3 again. So you'll see that it did a bad job, right? It couldn't distinguish between 3s, 9s, and 8s. And a 2 got sucked up in there as well. All right, take us home.
Okay. And then in the next one, so this is using ISOMAP, and this is going back to using PCA. So I'm gonna go ahead and run that, and then we can look at both of them. Oh, I'll just make this one smaller. Nelson, do you want to jump in again? Okay, I don't really know what to say about them though.
I mean,
they look different.
So the thing you can notice is that, so let's make one of them big. I don't care which one.
Okay. Like full screen?
Sure.
Or just, okay. Never mind.
There you go. Okay, so now if you look at this, you'll notice that there's a cluster in sort of the bottom center of this image in both the actual and predicted values, right? And that are all the same color. So whatever digit that was that's sitting around like 0, -5, it seems to have gotten that one right, right? Now the points are different colors because again, it doesn't know which digit is which. It just knows, hey, I found a bunch of things that are all the same and I put them together, which is what this algorithm is designed to do. Now, if you look at other ones, like for example, I mean, you can see sort of other ones that are less obvious. Like on the, let's see, what is that? The right side of the sort of main cluster, like around 5, -1, right? There's another cluster that's green in the actual training and blue in the predicted ones. But again, it seems to have done a pretty decent job of identifying, okay, all of these things are like each other. So they go together and I put them all into a bin, right? Now, there are other places where it's had a rougher time, right? In that middle, it's just a big stew, and it's very hard to tell this way which one's which. But it's a pretty fair guess that some of them are right and some of them are wrong. We already know that it had a really hard time with 8s and 9s. So I'm guessing the 8s and 9s are going to be a mess in there. So anyway, they're just different ways of looking at it, different ways of trying to see how well your model did, which I think is the next thing you're going to talk about.
Yes. Okay, so confusion matrix. I was pretty confusion matrix about this too. It said about this is that it's evaluating like the performance of the model. And then it just concluded that it wasn't really a success. But then this block right here, so these are scores. So the only one that I actually understand is this one, because this one's the easiest one. That one is, it measures how similar the object is to its own cluster compared to other clusters from a range from -1 to 1. So if it's at a 1, it's like at its best match. Anything like the lower it goes, like the worse the match was. So the higher the number, the better. This is for homogeneity. So to what extent all the clusters contain only data points which are members of the single class? This is completeness. So it measures the extent to which all of the data points that are members of a given class are also elements of the same cluster. This is just like, this is, what is it, V-measure? So this is a harmonic mean between these two right here. Adjusted RAND, it measures the similarity between two clusterings and considers all pairs of samples and counting pairs that are assigned in the same or different clusters in the predicted and true clusterings. This adjusted mutual info is used to compare the clusters, measures similarity between data points in clusters. I don't know what this one is though. It didn't say anything about this. So I don't even know like why it's there. Maybe like it's like the overall score or something. I'm not sure.
So yeah, I mean, all of these are just different metrics. The one that makes the most sense to me is the confusion matrix. So if you look at the confusion matrix, what it's telling you is how many things it got right. So for example, what this is telling you, if you look at this first row in the confusion matrix, right? It's telling you that all 43 of whatever were in the training set, or the test set, sorry, were correctly categorized by the prediction algorithm, the k-means clustering algorithm, in around cluster number 0, 1, 2, 3, 4, 5, right? So it got all the 5s right. Yay, right? All the 5s are correct. But if you look at the next line, what it's saying is, okay, I put some of the, so I put 2, or let's see, this is the, let's see, they're going into the 0, 1, 2, 3, the 3s, right? I put 28 of the 3s in the right spot, but I put 7 of them in one wrong spot and 2 in another wrong spot. And you'll see there are others that it really struggles with, like the third row here, right? So probably those were the 8s. So it put 23 of the 8s together, but then it put 9 over here as something else, and 4 of them in with the 3s, and one of them over here and one of them over there. And anyway, it had a rough time with the 8s. But you can see as you go down which things it did well on and which things it sucked at, right? So for example, the worst one of the bunch here is, let's see, it's row 0, 1, 2, 3, 4, 5, right? Where it had almost a perfect split between confusing the 0s and the 8s. I'm sorry, and the 7s, right? It put half of them in the 0s and half of them in the 7s. So is it 0 or 7? Well, you can't tell, right? So this is useful because what it does is it shows you where your model worked and where it didn't. So if I were actually trying to implement some kind of handwriting recognition thing, what I would do is I'd say, okay, this method works great for, 5s. And it works really well for, 0s. And it works pretty well for, well, actually the 0s are bad too, because if you look, it put a bunch of things, it basically made 2 different categories for 0s, which is not helpful, right? But if you know both of those are 0, then, that's fine. So anyway, the point here is that this gives you a way to look at this, right? And the other metrics measure different things, right? So for example, depending on your application, you might be more interested in if you got close than if you got exactly right. And that's what for example, the homogeneity and the completeness mean, right? The completeness and the homogeneity scores are basically telling you, not if it's always right, but is it always close? And other metrics are going to tell you other sorts of things, right? And you can go through and look at them, and there's all kinds of different metrics. And the one you want is probably, buried in there somewhere. Okay, does that make sense?
Yeah, I didn't understand what the matrix was for. Like, I didn't understand what it was saying, but now it makes more sense than these scores.
Okay, first of all, yay, good job, Cindy. I suppose we should say if there are any questions.
Are there any questions?
All right, just more clapping. So the point of doing this, right, is not to say that, oh, you should always use k-mean algorithms, because most of the time in scientific applications, we're not interested in clustering things, right? But you could come up with situations where we were. So for example, I know people who have worked on this sort of thing in particle physics because different particles will have different detector signatures. And so these clustering algorithms can be used to try to predict when you have ambiguous detector signatures, they can be used to say, okay, well, there are certain known glitches, right? Does this look more like, I don't know, a pion or a known glitch? And you run this sort of clustering algorithm and you say, okay, well, all these things, these ones are glitches and these ones were actual pions. So you could imagine using these, but most of the time in physics, we're more interested in getting into the regression side of things, which is, but the basic point here is the same. What you want to do is go digging around in a machine learning library like scikit-learn, or you want to identify the algorithm you want, and you're probably going to need to try more than one. You're going to have to dig through the documentation and figure out how it works. You're going to have to play around with it. You're going to have to read up on things. You're going to have to dig through a bunch of the user guide, and eventually you'll come up with, hopefully, an algorithm that you can actually do what you want it to do. So that's all a very long way of saying, mostly what this was designed to do is give you a little flavor of the kinds of things you could do, right? And I'll just emphasize one more time that this is the exact opposite of a simulation. A simulation, we think we have the model, we need to generate the data. This is the opposite. This is saying we have the data, we need to generate the model that made that data. And, you know, they're complementary things, but they're not exactly the same. All right. So that's it. That's all I got. Let me just very quickly say that it was a pleasure teaching this class. I mean, this is like kid in the candy store for me. You guys are fantastic students. We've had good projects. We've done some really interesting things, and I've very much enjoyed teaching the class. So thank you all for taking it, even in this horribly weird semester. The other thing is just one more reminder about the final on Tuesday, and you know, have a good weekend.
Thanks, Dr. Nelson. See you Tuesday.
Oh, and I guess we're meeting with the Galaxy group briefly.
That's right.
Oh, yes.
I am here.